So our third speaker of the day is Lior Gishboliner from ETH, telling us something about removal lemmas. Okay, it's all yours.
Thanks a lot for the introduction and for the invitation. So I want to give kind of an overview of this topic of polynomial removal lemmas. And some new results are based on joint work with Asaf Shapira and Tomon. So let me remind you that the graph removal lemma that many of you probably know, the statement is like this. So we have two graphs, H is small and G has n vertices, and then we assume that G has epsilon n squared edge disjoint copies of H, so copies that do not share edges. And what the graph removal lemma says is that then actually G must have many copies of H, so it needs to have at least some delta, which is a constant depending on epsilon, times n to the number of vertices of H. So a constant fraction of all potential copies of H are actually copies of H. So an equivalent way of saying this is that if we have less than this number of copies, then we can make G H-free, we can destroy all the copies by deleting epsilon n square edges. And to see that this is equivalent, we can just take a maximum collection of H disjoint copies, then every other copy intersects one of them. So if we delete all of the edges of the copies in this collection, then there are no more copies of H. And this looks like a simple statement maybe, but in fact it's a sophisticated result. And one evidence for this is that the only way we know how to prove it essentially is via Semered's regularity lemma. And another evidence is that it has some interesting connections to other fields of math. So for example, to additive combinatorics. So as many of you might know, the special case where H is a triangle implies the Ross theorem that says that a subset of the integers that doesn't have an arithmetic progression with 3 elements must have a sublinear number of elements. And this result also has many generalizations. So this is what I'll talk about now. So this is just I'm stating the removal lemma again. And let me now tell you two generalizations of this. So one is the induced removal lemma, and here it's a similar statement, but now we have induced copies, and therefore to destroy them, we are also allowed to add edges. But else the statement is the same. And another important generalization is to K-uniform hypergraphs, and here the difference is that the number of edges we delete should be a fraction of n to the k. So for graphs, it's n squared, and in general, it's n to the k. And there is also an induced version of this hypergraph statement. So let me give you some motivation why we want to look at theorems like this. So suppose we have a very large graph, and we want to know if this graph is triangle-free. Now, the graph is so large that we cannot go over all of the graph, so we have to relax the problem. So let's say we only want to distinguish between two cases. One case is that the graph is triangle-free, and the other case that the graph is far from being triangle-free. So what is epsilon far? It means that we need to delete epsilon n square edges to make it triangle-free. So we want to distinguish between those two cases. And here is a trivial algorithm to do this. So let's just sample Q vertices and check if the sample is triangle-free. So if we don't find any triangle in the sample, we say that the graph is triangle-free. And if we do find a triangle, then we say that the graph is far from being triangle-free. So why does this work? So the algorithm is trivial, but the analysis is not. So one direction is easy. If G is triangle-free, then the algorithm will say this with probability 1. But the other direction, we need the removal lemma. So if G is epsilon far, then by the triangle removal lemma, we know that it has delta n cubed triangles. And then if we sample something like 1 over delta vertices, then we will find a triangle with high probability, right? Let's say 0.99. And the reason is that if we sample 3 vertices, then they will make a triangle with probability delta. So if we repeat this 1 over delta times, then we get constant probability. So we see that the removal lemma just corresponds to this testing algorithm, shows that this testing algorithm works. And the bound that we have in the removal lemma, so this delta, tells us how many vertices we need to sample. So there is a kind of a big generalization of this result that holds for any graph property, hereditary graph property. So let me tell you what this means. So hereditary property just means that it can be characterized by forbidden induced subgraphs. So these are all the natural properties we know in graph theory. So for example, being A-colorable, being triangle-free, being perfect, being a chordal graph, and so on. And the result by Alon and Shapira is that a similar removal statement is true for every hereditary property. So for every property P and for every epsilon, if a graph is far from P and we sample some number of vertices Q, where Q only depends on epsilon, then with high probability, this sample will not satisfy the property. And this allows us to have this testing algorithm for every property, right? Because the algorithm is, again, trivial. It will just sample and check if the sample satisfies the property. And here, because we are dealing with induced copies, then again, the epsilon far is defined in terms of adding or deleting edges. And this was also generalized later to hypergraphs by Rödel and Schacht. Okay, so now what we can ask is, what is the dependence on epsilon? So we have a very general result. We know that for every property, we can test it with this algorithm, but we want to know how many vertices we need to sample. So how does this depend on epsilon? So unfortunately, all of these results, the proofs use the regularity lemma, or even some stronger version of the regularity lemma. And therefore, the bounds that we get on delta or on Q are very large. So even, for example, for triangles, the best bound due to Jacob Fox is that 1 over delta is at most a tower of exponents, so 2 to the 2 to the 2 to the 2, and the height of this tower is log of 1 over epsilon. So it grows very, very quickly with 1 over epsilon. So it's a major problem to improve this bound. The problem that we will care about is when does delta depend polynomially on epsilon? So in other words, when do we have an efficient testing algorithm? Where efficient means that the complexity depends polynomially on 1 over epsilon. So this is a general problem. Let me tell you some things which are known. So first we can look at the graph case and at the non-induced case. So we have the H removal lemma, and the result is that we can have a polynomial bound if and only if the graph is bipartite. And in fact, if it's not bipartite, then we have this upper bound. The delta is at most epsilon to the power of log 1 over epsilon. And this is smaller than any polynomial. Okay, so what happens when H is bipartite? So let's suppose that our graph G has epsilon n squared edge disjoint copies of H. So in particular, it has at least epsilon n squared edges. And then by the Kováry-Sós-Turán theorem, or by supersaturation, the graph has poly epsilon, so something polynomial in epsilon times n to the number of vertices copies of h, which is what we want. So we see that when h is bipartite, we do have polynomial dependence, and it easily follows from Kováry-Sós-Turán. And similarly, if we look at k-uniform hypergraphs, then and our hypergraph is k-partite, then we have polynomial dependence by the k-uniform variant of Kováry-Sós-Turán. Okay, so it works the same way. But for graphs, we also know that this is necessary. So that if the graph is not bipartite, then we don't have polynomial dependence. And here, the question was if the same is true for hypergraphs. So Hayakawa, Nagel, and Radel, they suggested that this should be the answer. And they also proved the special case where H is the clique, so the k-uniform clique with k plus 1 vertices. And then there was some work of Alon and Shapira, and they proved partial results. So they proved for a large family of hypergraphs H that delta is not polynomial. And finally, with Asaf, recently we managed to solve this problem. So now we can show that this is indeed the answer. So for k-uniform hypergraphs, we have polynomial dependence if and only if H is k-partite. And the plan is to show you the proof of this theorem in the second part of the talk, if there is time. So let's move on to the induced setting. So now we look at the induced removal lemma. And here there were also previous results. So there was this theorem of Alon and Shapira that gave an almost complete characterization. So PK is the path and CK is the cycle. And so P2 is just an edge. And they showed that if H is an edge or a path with 3 vertices or the complement of one of these graphs, then we do have polynomial dependence. But if H does not belong to this family of 7 graphs, then we do not have polynomial dependence. Okay, so this is usually the situation for the induced case, that there are just finitely many graphs where there is polynomial dependence and everything else doesn't have. So because we are in the induced setting, a graph is equivalent to its complement because we can always take complement. So what remains is P4 and C4. P4 was solved by Alon and Fox a few years ago, and the only remaining case is C4, which is a very interesting open problem, I think. And we believe that it should also be polynomial. And the reason is that we have a bound which is much better than the tower bound. So with Asaf, Shapira, some time ago, we improved the bound from tower type to exponential. And a more general problem, which would be very interesting to solve, is to characterize now graph families. So instead of a single graph, to look at finite graph families and understand when the induced H removal lemma is polynomial. And the key open case seems to be when H is just one graph, just C4. Now let me say something about hypergraphs. So there was another result of Alon and Shapira that if we look at k-uniform hypergraphs where k is at least 3, then the induced removal lemma bound is not polynomial unless, well, there are 2 cases. One case is that the number of vertices of H is k. This means that H is an edge or a non-edge. So this is a trivial case. And the other case is that there is a specific 3 uniform hypergraph. This one here, it has 4 vertices and 2 edges. And for this case, they also didn't know the answer. And with Istvan, we proved that for this hypergraph, we have polynomial bounds. And it's kind of interesting because we had to understand the structure of hypergraphs that do not contain this thing as an induced subgraph. And it turns out they have kind of a simple structure. So you can always find the partition of the vertices into 2 parts, let's say X and Y, such that if we look at the edges that intersect both X and Y, then either almost all of the edges are present, all of the such edges are in the graph, or almost none of them are in the graph. And then we can continue decomposing inside of X and inside of Y, so we have some iterative structure like this. Okay. Now I want to say something about ordered graphs. There is also an interesting question here. So recently, there was a result of Alon, Ben Eliezer, and Fisher that proved that the removal lemma and also the induced removal lemma, so all the results we saw, hold for ordered graphs. So ordered graphs means that, well, it's the same, but now a copy of H must respect the order of the vertices. And this is actually a complicated proof. It's much more complicated than the unordered case. And they asked, when is the removal lemma polynomial for ordered graphs? So with Istvan, we could prove some results towards this question. So we looked at the induced case. We look in the induced H removal lemma, and what we showed is that, well, there are essentially 2 cases where it's polynomial. One is the trivial case, where H is edge or non-edge, and the other case is when H is this path, ordered in this way. And this is also kind of interesting because up to now, the proofs of polynomial removal lemmas, they relied on results that said that graphs that satisfy certain properties, they have small regular partitions. So as you might know, the semi-ready regularity lemma says that every graph has a regular partition, but the size of the partition is very large, right? It depends. It grows as a tower in 1 over epsilon, and therefore we get these bad bounds in the removal lemma. But there are results that if a graph has certain properties, so if it does not contain certain H, let's say as a subgraph, then it has much smaller regular partition. So partitions of size polynomial. And this can be used to prove removal lemmas. And most of the examples up to now were like this, that using such a efficient regular partition, you can prove a polynomial removal lemma. But in this theorem, this is an example of a case where we can prove a polynomial removal lemma, but the graph can have, but graphs that forbid this path P can have very large regular partitions. So they can have also partitions of only tower types. Okay, so here's a question. So what should be the characterization here for the non-induced case? So we look at ordered graphs, the non-induced H removal lemma, and we ask what the characterization is. And here's a problem. So prove that if H is an ordered forest, then the H removal lemma has polynomial bounds. So we know that if this is true, then we have a characterization. This is okay. So this, I don't want to say the characterization because it's a bit complicated, but this implies that the characterization is correct. Okay. So maybe, are there any questions until now? Okay, then let me go to the proof. Let me tell you one proof. So this is the theorem that if, so we have a K-uniform hypergraph, it's not K-partite, then the H removal lemma is not polynomial. So first I want to tell you the Rouge-Semerer deconstruction, and this is our method of proving that the removal lemma is not polynomial. So every such proof uses some variant of this construction. So I want to tell you the basic construction. So we take a set of 1 up to n that doesn't have a 3-term arithmetic progression. And by a result of Berend, we know that there exists a set like this of size n to the 1 minus little o of 1. And then we construct a 3-partite graph as follows. So the 3 sides roughly correspond to the integers 1 up to n. And then for every x in 1 up to n, and for every s in our special set, we put a triangle on the vertices x, x plus s, and x plus 2s. So why is this construction good? So first of all, observe that, that these triangles that we put are edge disjoint. They cannot share 2 vertices. And this is because if you tell me 2 of these 3 vertices, so for example, if you tell me x plus s and x plus 2s, then I can find x and s. So there is just a unique triangle containing each edge. And the second good property is there is no other triangle. So the only triangles in the construction are those that we put in. So let's prove this. Let's suppose that some xyz is a triangle. Then, okay, why do we have the edge xy? Because y minus x must be some element of s. Let's call it s1. And similarly, z minus y must be some element of s, let's say s2. And z minus x must be 2 times some element of s. So let's say 2 times s3. So then we see that s1 plus s2 equals 2 times s3. But this is the equation of a 3-term arithmetic progression. So this is only possible if S1 and S2 and S3 are all equal, because otherwise we would have a 3-term arithmetic progression in S. Good. So we see that that the only triangles we have are those original triangles that we defined. So we managed to pack many triangles without creating new triangles. So why is this good? Well, we can choose n. Okay, now let's say we are given epsilon. Now let's choose n such that S has size epsilon n. Then, because the size of S is n to the 1 minus little o of 1, if we solve this, we see that n is epsilon. So n is super polynomial in 1 over epsilon. And now, okay, now we can, we can estimate how many triangles we have. So we have epsilon n squared edge disjoint triangles, because we have 1 triangle for every x and s, and we have epsilon n squared such choices. But the total number of triangles, if we write it as a fraction of n cubed, then it's n cubed over n, and n is a super polynomial, so we get something which is smaller than any polynomial in epsilon times n cubed. So this construction shows that the triangle removal lemma is not polynomial, right? So we have epsilon n squared edge disjoint triangles, but the total number of triangles is, as a fraction of n cubed, is smaller than any polynomial. Okay. So what we need is that a similar construction also holds for odd cycles. So let's say we want a construction for C5. It's very similar. We just take x, x plus s, x plus 2s, x plus 3s, x plus 4s. and we put a cycle of length 5. Okay, and the analysis is essentially the same. And in fact, this also works if this also works for even cycles, but only if we care about cycles that look like this, that they go from V1 to V2 to V3 to V4 and so on. Because of course, we can have cycles between two of the parts, right? Between V1 and V2, for example, and we don't have any control of these cycles, but we do have control of cycles that go V1, V2, V3, and so on. And there is also a construction, so a generalization of the triangle for K uniform hypergraphs is the clique on K plus 1 vertices. And there is also a construction for this clique. So what does this construction do? It gives a K uniform hypergraph with epsilon n to the K edge disjoint copies of this clique and with no other copies. And as before, n is super polynomial in 1 over epsilon. Okay, so those are the ingredients we need for our proof. This is the theorem we want to prove. And so to prove it, we will have two cases which we can solve, and then we will see that those two cases actually cover all the cases. So here is one case. We assume we look at the two shadow of H. So this is a graph where two vertices are connected if they are contained in some edge of H. And we assume that this two shadow has a cycle 1 up to L, such that every other edge intersects the cycle in at most two vertices. Okay. So what we will do in this case, we'll kind of reduce the problem to the Rouget-Semeredi problem for cycles. So we will take the Rouget-Semeredi construction for the L cycle that I showed you on the previous slide, and we will kind of add some things to it to make it a construction for our hypergraph. So let's take this Rouget-Semeredi construction. It has L parts, each of size n, and it has epsilon n square edge disjoint cycles of this form, V1 up to VL, where Vi is in Vi, and there are no other such L cycles. So let me denote this collection of cycles by C. And we also know that n is super polynomial in 1 over epsilon. Good. So now we want to add more parts. So let's denote by small h the number of vertices in big H. So we want to have H parts. In the end, we want to take copies of H that have one vertex in each part. So we add the remaining parts, also of size n. And now we want to have some family of H tuples on which we put copies. So I want to tell you on which H tuples we want to put the copies. And this claim tells us that there is a family of H tuples with some nice properties. So here are those properties. First of all, the size of the family is epsilon n to the K. Then every such H tuple has to extend one of the cycles. So if we look at the first L coordinates, it's one of these cycles in C. Now, and we have two more properties. So the second is that if we look at two tuples that extend the same cycle, then they can share at most K minus 3 vertices. And the last property is if we look at two H tuples that extend different cycles, then they can share at most K minus 1 vertices. So this maybe looks strange. I'll show you in a second why this is useful. The proof of this claim is just a probabilistic alterations argument. So for every cycle and for every way of extending this cycle, we add this tuple into H with this probability. And then we maybe have some pairs that violate items 2 and 3, so we just delete them. And if we do the calculation, then the number of tuples we delete is smaller than the size of the whole collection. So it's just the usual deletion method. Okay. So now, why is this useful? So here is the construction that we use. We take this set of H tuples that the claim gives, and we put a copy of H on each of them. And now we claim that these copies are edge disjoint, right? We want many edge disjoint copies, but not too many copies in total. So let's assume that two such tuples share an edge. Now, an edge is K uniform. It has K vertices. So these tuples share K vertices. Now, by the third item, if they extend different cycles, then they cannot share K vertices, so they must extend the same cycle. So if we look at the first L coordinates, we have the same points. Okay. But now, by the second item, the last H minus L coordinates can have at most K minus 3 common points. But because there are K common points, at least 3 of the common points must be in the first L coordinates. So in other words, this edge E must have at least 3 vertices from the first L coordinates. But this is impossible, right? Because we assumed that every edge intersects this cycle, 1 up to L, in at most 2 vertices. So this cannot happen. So we see that the copies are indeed edge disjoint. And now we want to bound how many copies we have in total. So to do this, we prove that if we take any H copy in this construction, and we look at the first L coordinates, then these L coordinates form a cycle from our collection. So I will not have time to prove this. It's not very difficult. But given this claim, we can bound the total number of copies, because we know that every possible cycle belongs to our collection. This is the guarantee of the Roger-Semmer deconstruction. So in order to choose a copy, we need to choose a cycle, and then we have n, at most n options for any other vertex. So we have this C times n to the H minus L, but C is at most n squared, and L is at least 3, so we can write that this is at most n to the H over n. But since n is super polynomial in 1 over epsilon, like before, we see that this fraction of n over n to the H is smaller than any polynomial, which is what we wanted to prove. Okay, so this is one case of the problem that we can solve. Here is another case, which is similar. So let me walk you through this. So we take some integer s, which is at least 3, and we look at the s minus 1 shadow. What is the s minus 1 shadow? It's an s minus 1 uniform hypergraph, where a set is an edge if it's contained in an edge of H. So let's assume that this shadow has a clique on S vertices. And let's assume that every edge of our hypergraph intersects this clique in at most n S minus 1 vertices. So it does not contain the clique. Then I claim that in this case, also the H removal lemma is not polynomial. And this is very analogous to the previous case, and the proof is very similar. The only difference is that instead of using the Roger-Semmer deconstruction for cycles, we use the construction for hypergraphs, right? The construction for this clique. Okay, so those are two cases that we can solve, and now I claim that every case falls into one of these two. So let's see this. So let's take the 2 shadow of H. This is a graph. Now, if this graph has an induced cycle of length at least 4, then because the cycle is induced, every other edge intersects the cycle in at most 2 vertices, because otherwise there would be a triangle in the cycle. So in this case, we are done by the first case. And else, this graph is chordal, right? Now, what we also know is that H is not K-partite, and this exactly is equivalent to G being not K-colorable. So H is K-partite if and only if the two shadow of H is K-colorable. Okay, it's a basic property. So G is not K-colorable. But chordal graphs are perfect. So if G is not K-colorable, it must have a clique of size K plus 1. So let's call this clique X. Now let's take a subset of X, let's call it Y, which is minimal among all subsets that have the following property. There is no edge of H that contains Y. Okay, let's take a set that is not contained in any hyperedge and is minimal with respect to this property. So why is there such a Y? Well, X itself is not contained in any edge because X has size K plus 1 and edges have size K. And also, Y has size at least 3 because X is a clique in the two shadow. So every pair of vertices is contained in a hyperedge. Okay, but now if we denote the size of Y by S and we look at the S minus 1 shadow, well, we know that every proper subset of Y is contained in a hyperedge. So this shadow forms a clique, but also Y itself is not contained in any hyperedge. So, so every edge intersects Y in at most S minus 1 vertices. So we are exactly in this second case that we knew how to solve. Right, so this shows that indeed we cover all the cases, and so this is the proof. Okay, so this is everything I want to say. Thank you for your attention.
Let's thank Lior for the nice talk.